Okay, we're talking today about chapter 4. Chapter 4 deals with central tendency and variability. So we talked now about various things. So we talked about how to aggregate data. We talked about frequency distribution. We talked about how to show this data graphically, how to mark them into different ranges, how to describe frequency distribution. We talked about graphical ways how to display data. We looked at different forms of graphs. We learned for what data we were recommended, or which graph is recommended for what type of data. And today we're going to go further in detail into how to numerically aggregate these data. So as you remember, we had with the frequency distribution, the histogram shows each individual numerical value that is found in your data. Then you had frequency tables that basically was a numerical tabular depiction of this visual data from a histogram, shows for each individual value the frequency of occurrence. For grouped frequency tables, you basically have intervals and you count the number of occurrences within that interval. That kind of gives you an idea how to aggregate data. And now there are different ways how to aggregate data that basically collapses this multidimensional data over all these rows that are available to one numerical value, and shows in addition to that not only this one numerical value describing that distribution, which is a normal distribution, as you remember, normal distribution, symmetric, bell-shaped, and unimodal with only one peak. So you basically you show how does that normal distribution look like with numbers, with two numbers. One number reflecting where's the center, and the second number basically describing how does it distribute, what's the variability in my data. And with the idea that all of this basically is a reflection or basically aggregates a distribution that is consistent with a normal distribution curve, symmetric, bell-shaped, unimodal. So central tendency and variability, and central tendency is really that you mean to describe the center of your data. That's essentially what it is. And the variability is the variability of your individual data points around that center. And there are various ways how to do that. Okay. The descriptive statistic that best represents the center of a data set, the particular value that all the other data seem to be gathering around. Okay, so these are Nolan and Heinzen's words. So we will discuss 3 different measures of central tendency. We're going to be discussing an arithmetic average, the so-called mean. We will be discussing the median, the so-called middle score, and we will be discussing the mode as the most common score. So these 3 are substantially different, and this is where we have now the Charity Navigator score data. So this data is in the Excel spreadsheet, and there are, let's look at it right now. Let's look at it right now. So we have this data set here. These are all the scores here. We have scores that are basically ascending in value. So they're from 100 to 0, with 100 being the best entry. We can now start off by basically looking at this data. So you have your entries that are somewhere in the 90s. There are some in the 80s. There's even one in the 70s, which is not that great of a charity probably. And this is our distribution. So we have the last entry is at 41. So these are 40 minus the header. That's 40 entries. So we have data of 40 charities. And this is basically what Nolan and Heinzen has shown here with this graph. And they are showing here basically already with a yellow arrow, they're showing the mean. So now the mean. So we have the mean, the median, and the mode. These are the three markers of central tendency we're going to discuss today. As you all know you all have discussed this in high school. So basically the mean is calculated as the sum of each individual entry. So each individual charity's score is being added together with all the other scores, and you divide them by the number of entries. And that is the mathematical formula. So you have basically M as the mean equals the sum. So this epsilon basically indicates that it's a sum of all individual X. So X, when you see an X of that kind, this always indicates that it's an individual data entry. So I'm actually not super happy with X only. It's in more advanced statistics. If you read in real statistic books, it will basically say XI, I standing for a consecutive number. So you would have I basically ranges from 0 to the maximum number of observation. But for now, sum of X of all individual X values divided by the number of entries, which is N. N always indicates a sample size or a number of observations. So basically, when you have when you're doing that, you basically need in Excel to do nothing else but, okay, let's calculate the mean. So the mean is here the sum, and that is in Excel done with the sum function. That is SUM. And then you basically indicate the range that you want to sum up. So this is the sum from A2 colon A41. So you do A2 to A41. And if you make the parentheses, you get the sum. So this is 3,613. So we can actually move this a little bit to the side. Let's move this to column F. So this sum divided by the N sum. And now the N is basically count. It can be counted as A2 divided to A41 is basically 40, as we have determined before. So you can do this, obviously, you can also do this by just counting as I counted before. If you do it with the count function, it has one large advantage. Let's imagine you have a data set where you have empty cells. If you do the sum function, it will only sum those with an actual numerical value. If you just go by the number of rows, you may count those that have an empty cell also as one observation, although they're not contributing to the sum. And that's a problem because then your mean is off. So if you use the count function will only measure those cells that have a valid entry. So if I would take this out, count changes to 39. Just make sure that you kind of keep that in mind, because this is, again, soft coding, hard coding, same conversation piece. If you have a data set that may be changing or that may be incomplete, it's always better to take the count function, because Excel will do that job for you to determine whether there's a value in there or not and should be counted or not. So it makes a lot of sense to know the function per se. Good, and now we want the M. And the M is, as we determined before, the sum of all entries divided by the N. And this is here 90.33.
What was the equation?
Wait, let me copy that over. So you get this spreadsheet, then obviously I will post it as I always do. If I don't post the spreadsheet by the next day, at around afternoon, depending on what time I'm getting home, and get to it, please poke me, write me an email, let me know that I didn't post the spreadsheet yet. But I want you to have all this spreadsheet on what we're doing in class.
It's on campus.
Yes, I post the spreadsheet. The completed spreadsheet will be posted as a so-called announcement. You have seen my announcements, right?
Okay.
So I'm posting the lecture recordings as announcements, and I will post the completed spreadsheets as announcements.
Where do you get the F3 and F4 is just taking the total of the
Exactly.
Of 30, the 40, and then the...
Exactly. So it's basically the formula is you take F3, which is the sum, divided by the N. So this is consistent with this formula on the slide. So this is the sum of x of all individual x divided by the n. Good. Okay, so this is the mean. We also know that Excel has a lot of functions that makes life a little easier. That respective function in Excel that does the average or the mean is the average function. You do average parentheses A2 to A41. You get the same value. So we did it correctly. Good. So this is the calculation of our mean. Simple, right? Wait, let me already put that formula out. So it is the average function, average of A2 to A41. Okay. So this is the arithmetic mean. And what's the idea behind it? You want to have this central value. So you want to understand the distribution and you want to determine the function, the center. And you're doing that by having this arithmetic sum divided by the number of observations. Gives you an idea about the center. So now this distribution obviously not very pretty because it's kind of skewed here. It's negatively skewed, but it's usually with a symmetric unimodal bell-shaped distribution. This would be right in the middle, hypothetically, in a hypothetically perfect normal distribution. So now what is to be kept in mind, you remember the distinction between a population and a sample. So a sample is a subset of a population. When you quantify a mean from a sample, you're talking about quantifying a statistic. So statistics are basically shown in normal Latin letters. So you have M or X bar. Both is basically comparable. You will find both versions. X bar essentially also can present with an X and an actual bar on top of that X. That's why it's called X bar, because the proper way in statistics to show that this was an X bar. But yeah, it's for this class, Norden and Heinzen will refer to it as X bar or as M. If you have a mean of a population, and this is where it's becoming a little tricky, because you will have a Greek symbol, and that Greek symbol is called mu. So it's basically, it's like a U, and a handwritten U with a little bit of a longer handle on the left. So mu is basically indicating that this mean comes from a population. As you can imagine, this distinction is quite important, particularly later when we're comparing sample, central tendency and variability to population values that are both given in the question. So we have M or X bar and we have mu, but it's basically calculated in the same way. The difference is, though, for a population, calculating a mean for a population is obviously quite a task because you have a whole population. For a sample, it's usually a smaller fraction of the population. So in the questions, you will have your mu's given, and you will see that later on when we come to hypothesis testing. So the next marker of central tendency is the median. So the median is a little trickier. So when you think, can you remember last time we had the violin plot? On Monday, we talked about, that was the last slide. Before we concluded the class, we talked about the violin plot that basically showed the distribution in a vertical format. And we had a box whisker depicted vertically. And that box basically contained in the middle a white dot, which is the so-called middle score. The middle score is consistent with the median. So basically what the median does, it splits the data in half. So you have 40 entries, your middle scores is basically splitting the data in 20 above that value and 20 below that value. So this being said, you need to approach the median differently than the mean. It's not an arithmetic calculation. Well, it is essentially one Excel makes an arithmetic calculation, but basically you make it different because you take your data, you sort your data, and by sorting it, you basically can go ascending and you find that value that literally splits the data in half in magnitude. So you follow the magnitude up until a magnitude that literally numerically splits the data in half. And there you obviously have a situation that you have so if you have an odd number of entries and you have, let's say, 41 entries, it's considerably simple because then you just have one value splitting the data in the upper half and the lower half. If you have an even number of scores, you take the average of the center two score values. So you build the average and that is your median because it splits them exactly into half below and half above. So how we're doing that, we have such an example with our Charity Navigator score. So we can now just insert the line, one column. So this is now a running ID. We can do 1, 2, 3. We select these 3 entries and we go again on the right lower corner. We, click on top at the A and make a right click and you get this pull down format. If you say here insert, it will insert one column and it will shift the whole thing to the right. Yeah. Just do it, be bold. If it goes wrong, just press Control and C like zebra and it goes backwards. So please play around, do these things. That stuff that I'm doing at Excel, please don't hold back, just do it. You get the initial spreadsheet and you get my completed spreadsheet. Don't hold back and do your own attempts to solve the problem, because these whole exercises are basically for you to practice. And I guarantee you, no matter what you do down the road, knowing Excel will be super helpful to you. For you. So if you have a consecutive series, like you have here, 1, 2, 3, and you go to the, so just start this off, write ID, write 1, 2, 3. If you go then to the right lower corner and you double click that corner, you basically get all the way down and it will complete that series up until the last entry. Right lower corner, double clicking. And that will complete the entire series and saves you a lot of work. You don't even have to scroll or anything. It's just does everything automatically. Good. So why did I do that? Because now we want to do the following. Now we go on, we're selecting A and B. So like if you click here on top and you select A and B, you basically, you get the entire column selected. And that is true up until the last very entry, which is like 40,000 or something. So it will select the entire column. Then you click on data. You click again on sort. And now you sort by, make sure that my list as headers is activated. And you're sorting this by your actual score. So you sort this by score, you get smallest to largest. When you do that, it will sort it, starting with the lowest entry, all the way down to the highest entry of 97.9, I think is the highest. Why do we do that? Because we want to now determine the middle score. Why was this important to be done? Why did we need, well, we do it for the middle score because now we can actually find the middle score. Why did we label it with ID? Because there may have been a reason why the data came in at that format and you want to preserve that ID because it may have been a chronological order in which it was assessed or whatever. So it's always good to kind of attach a running number to your individual entry, because by that you can always restore the initial order. So keep that in mind. Always make sure you have a systematic approach to things that brings you back to the root data, to the data as it was initially. You select A and B, you go on sort, You sort it by column. You make sure that my list has headers is checked, and you click OK. Then it will sort it. So we have now 20 entries. So now we know we have 20 entries, and we have altogether we have. So if we're doing this now, okay, so we do now ID2. ID2. So if we do 1, 2, 3 again, so this is now in terms of magnitude, we create a new ID. You don't have to do that. Practically, you don't have to do this, but basically it makes it easier because now you have 2 fields that you want to quantify. And these are the middle 2 values. So if you are interested in quantifying that middle score needs to be between 20 and 21, right? Because it splits your data in 19 below, 19 above, and then you basically, the middle 2, you build the average between those 2, which is now 90.15, that will split it in an upper half and lower half. Does that make sense? Yes.
Why you do the 20s when we learn about 19 and 20?
Well, because if I do 19 and 20, then I only have 19 for the upper part, right?
But it's like uneven in one direction.
Okay, let's test this. Let's bring this to the test. Let's say median B2 to B40. It's 90.1. You're right. It's 19 and 20. Yeah. You're right. I agree. I agree. No, I had a miscalculation. You're right. It needs to be 19 and 20. So it needs to be the average between those 2. 19 and 20, and of course, because you're selecting the lower 20 and the 1 counts as 1. Yeah. Okay. You're right. Okay, so you create the average between these 2. That will basically get you now the median. So now we do median. You do average of these 2. And basically this leads you to that middle score. So that stratifies you now in the upper 50% and then lower 50%. Good catch. Thanks for correcting me. Yes, please.
I don't get what the 1920 has to do with the 90.1.
So this is the value that is found for both 19 and 20. So you need something that splits this data set exactly in an upper part and lower part. So if you have exactly that value of those 2 and you're building the average, this will automatically sort it in upper and the lower part.
So let's say there's different numbers.
Yep.
The same numbers, they're both the same.
So let's say, so this is why I was misled, because I had in the back of my head it was 19.15. So if you had this 19.2, then this would be 19.15. So now it's easier because now it really splits it in the middle, right? Since it was 90.1, it's kind of like ambiguous, but that's just the rule of how you approach this. So this middle part will basically become the median. So it's 90.1. Yes.
What's the point of the median? Why did you choose 19 and 20? Because before you said 20 and 21,
yeah, that was my mistake, which yeah, there was.
But is it depending on? Let's say we have 40 like values here.
Yeah.
Why don't you just choose 20? Because that would also be an equal split. Like, why don't you choose 2 of them?
Because then you have an unequal number in both groups. So you need to find the 2 middle scores that basically that are at the higher end of the lower 50 and at the lower end of the upper 50. So you need those 2 scores. And you need to determine those scores, and that's kind of catchy. The other way how to do that is with the median function, where Excel is doing that for you. Yeah. Yes, please.
I'm not so sure I'm right. Did you do this B2 to B40?
Uh-huh.
B2 to B41.
B2 to B41. Oh, it's 41. still the same. Has to be the same because now it would take an unequal number. So now it will only count 39. And that would again render the 90.1 in the middle score. So, but you're right, the formula was, God, like, median, it throws me off that entirely. So we have, so median, you're right, it's B2 to B41. That's a good catch.
It's fine, I get 19.15 when I did that.
Okay, so maybe my first approach was actually correct. I just got thrown off by this. Okay. So we have 20 entries. We have 20 entries below. Yes, actually, yeah. So I was right initially. You showed me off. Okay.
Odd number.
Yeah, well, exactly. When it's odd numbers, it's super easy, right?
Like the average of all the middle number of the middle, not two middle.
Of the two middle numbers, because you're only splitting it in two. So there's one at the lower. You take the lowest value in the upper 50%, and you take the highest number in the upper in the lower 20. The highest in the lower 50%. So you take these two and you build that average, and that gets you, hypothetically, it gets you between those two numbers, and thereby it's automatically stratifying in upper and lower.
I guess I still understand why it would be three, with the three middle numbers.
No, it's two numbers.
Okay.
Well, it's 50%. It's higher 50% and lower 50%. Higher 50%, you take the lower number, the lowest number, and you basically take in the upper, you take the highest number. So you can test this essentially. If you just have, if you take min of the upper 20%, of the upper 50%, you get here minimum. Oh, well, you get B. So this is 90.2. And if you take max of B2 to B21, that would be the maximum. So it's the max of the lower 50% and the min of the upper 50%. This one? Yeah. Okay, so this is this. This formula is this formula. And this formula is this formula. Okay. So that's the calculation of the median. Okay. That was a little not so smooth. Okay. So basically, if you do it that way, you get that median that basically allows you to describe that center of your distribution. So why is the median a good value, a good measure of the metric? Because the median, in the end of the day, has a huge advantage over the mean, and we'll talk about this in more detail. Because the mean, because it's arithmetically derived from a calculation, as soon as you have an outlier, that means one extreme value in your data set, you will automatically have a changed mean, or you will have a mean that is away from the actual distribution of the actual frequency distribution. And this is one of the common quiz questions, and we will discuss this a little later on the slide. If you have data that is quote unquote skewed, so you have extreme values, you have outliers, the mean will always be shifted away from the median, because the median stays considerably stable and doesn't really deviate from the actual frequency distribution. But the mean will always be pulled towards your outliers. Arithmetically has to be, because it becomes part of the sum with an equal number of entries. So it will basically be shifted away from the median towards the actual outliers. In a normal symmetric distribution, you will basically have a mean and a median that is identical. If it were a perfect normal distribution. Yes, please. Exactly. A positive skew would mean that the mean is greater than the median, and negative skew would mean that the mean is smaller than the median. Correct. Because arithmetically, it will shift in that direction because the sum is either smaller, gets smaller, or with a positive outlier, the sum gets larger, but it's still the same number of observation in your data. So calculating the mode. This is kind of the same exercise, but what you do now with the mode is basically the most frequently occurring data entry. So this is basically on your normal distribution. This would be the very center, the peak of your normal distribution curve. Here in this context, the mode would here be 92.5. So that would be the highest bin, so to say. So that's the most frequently occurring value. We're not going to calculate the mode. There are some functions to do that, but it's rather a very rarely computed value. It's only in some certain very specific use cases where you would need to calculate a mode. You may see some of the quiz questions asking you determine the mode, but then it's like simple. It's like 8, 10 different entries, and you just need to see which one is most often occurring. So it's usually quite an easy question. So, so when you would think of mean, median, and mode on a normal distribution curve that is symmetric, bell-shaped, and has one mode, the mode, the median, and the mean would be exactly at the same point, and they would not deviate. Only if you have outliers, then the mean starts to deviate first. The median, if you have a lot of outliers, then the median starts to shift at one point. But what most of the time on your normal distribution remains rock stable, that's the mode. Because the most often occurring value, mostly, even if you have data that has a lot of outliers, the most often occurring value is usually quite the same and quite often occurring, and the mode doesn't really move much. So neither median or mode has an abbreviation. What is important with the mode is used for visual inspection of data and the visual characterization of data. So if you have a normal distribution, it's simple. It's unimodal. It means there's one mode. However, you have in many situations, you have also a bimodal distribution or a multimodal distribution. Can be for various reasons. The example that Nolan and Heinzen shows here is the bimodal distribution of women with the name Violet. So it seems that there was quite a peak of babies that were named Violet in the 19th century. And then later on, there was a renaissance of the names, like somewhere in the early 2000s. So you basically have a bimodal distribution of women that lived in the US with the name Violet, which is typically a bimodal distribution. You get this also in the context of different parameters. So when you have a situation like that, although it's the most frequently occurring value is basically here somewhere around 2010, you would still kind of characterize this as a bimodal distribution because you have two distinct peaks, and you would still refer to them as bimodal because it's basically a way to characterize this data. You would have different use cases or different scenarios where you would see a bimodal or multimodal distribution. Is usually when you look at a distribution that has very distinctive features. Let's say, for example, when you look at inflammatory markers. You would have a majority of people does not have many inflammatory markers, and then you have that bulk that actually had no ongoing inflammation, and their inflammatory markers are high. Same with blood pressure. So there are various scenarios where you could see that. So this is unimodal, bimodal, and multimodal. Multimodal is basically a scenario where you have several of these modes, and you have several independent occurrences and several independent increased frequencies over the entire range of your data. So mean is a arithmetic mean that basically is the sum divided by the number of occurrences. Very reactive to outliers. As soon as you have outliers, don't trust the mean. Which is important to keep in mind, because you always should, in your descriptive statistics, do a mean and a median, because the comparison of those two, just by the numeric value and the numeric difference, gives you an idea about how the distribution looks like and what outliers you may need to pay attention to. With the mode, you have a way to visually characterize your distribution, and can be either unimodal, bimodal, or multimodal. Any questions? So, and now we're coming to this topic. So if you have now a situation like that, where you have the charity navigator data, and you have the lowest rated charity included. So the data set that you have from me is not including that charity, which I'm not really sure why that charity is rated that low, but it's an outlier. It's a negative outlier that basically would, if you do a frequency polygon, skew the distribution negatively. Well, it likely wouldn't really, because the function would smooth that out if it's just one charity. But what happens here, and that is really the tricky part, you have a very strong weight on that outlier, because it will contribute disproportionately large to the sum, while not changing the number of observations, and thereby not changing or thereby changing the calculation of the mean. So you can't really say what's best, mean, median, or mode. That's very hard to say. It really depends on the distribution, and it's always recommendable to do both. With outlier data and non-normally distributed data, you would usually gravitate towards using the median rather than the mean, for obvious reasons, right? So if you exclude an outlier, and this is very hard to do, because excluding an outlier really requires a very strong justification for doing that. If you exclude an outlier, you basically get a more realistic estimate of your mean that basically will be closer to the mean, closer to the median again. But again, excluding outliers is, in science, a very complicated thing to do, because the justification needs to be very solid, and you need to have really a good justification and good reasons why you would do that. Because sometimes even those outliers have some pathophysiological meaning that you actually should pay attention to. So it's not as easy to just create a sneaky sample, as we discussed with the graphs. You actually need to justify each individual point that you're excluding. Okay. So which measure of central tendency is the best? The mean is really the most commonly used marker of central tendency, and it's basically really suited for symmetric distributions, or distributions that are somewhat consistent with normal distribution. The median is good for skewed distribution, or those with one or more outliers. Highly recommend to always compute both. As you see in Excel, it's basically it's a second cell, it's a second function, and you get both at the very same time. So our data actually seems to be somewhat close to normal distribution, because we have mean and median are actually not that terribly far apart. With 90.3 versus 90.15, it seems to be distributing quite well. We can actually show this. We did a histogram the other day. So if we can insert And to show this data as a histogram, we can basically look at this data. Like this. So we can basically change the bins. At the performance data series. On the flow bin, we can change the bin width to, let's do this in like 8 bins. So we can show this data with more bins. Gives kind of a better idea of the bin distribution. So this is how you build histograms with the totality. And yeah. So the mode is basically used in 3 cases. This is when you have one particular score that dominates the distribution. When you want to describe your distribution as either bimodal or unimodal or multimodal, and when the data is nominal. So when you have nominal data that are depicting the frequency of, then you would refer to the bin with the highest frequency as a mode. But as said, it's usually it's not the most common way of expressing central tendency. Good. Any question on central tendency? If not, then we can move on. So mean, median, mode, and then we have variability. And variability is super important because in the end of the day, the way you're describing your data will be with a mark of central tendency and a mark of variability. So now for variability, you can do this in various ways. The easiest one is basically by quantifying the range. So the range of all the data is basically the minimal value and the maximal value, and the numerical distance between those both. So basically, if you were to calculate this in your data set, so let's bring this up. So with Control and X, you can basically copy paste. So you can basically move things around. If we were to calculate the range, we would need to understand min from A2 to A41. No, not A, B. B2 to B41. And so this would be min, then we need max, and that's max of B2 to B41 is 100. That's 100. Wow. Okay, so now the range is basically the difference between those two. And this would you basically would calculate distance between those two, and the range is now max minus min. That gives you the range, which would here be 28.5. So this is all considerably simple. Where it's becoming now more interesting is when we calculate variance and standard deviation, but I think we first calculate the interquartile range. And now it's getting a little bit more technical. So range is highest minus lowest. The interquartile range becomes more interesting. If you have 40 entries, you have 20 in the lower 50% and 20 in the upper 50%. If you further stratify this, you're basically getting quartiles. So you can say the lowest 10 entries is the lowest quartile. The next quartile are number 11 to 20. Then you have the third quartile that basically would be 21 to 30. And then you have the fourth quartile with 31 to 40. So you basically substratify this. So once you have 50% lower and 50% higher, The only thing you need to do, you're creating a median of these subsets. So that will split it in 4 equal parts. And that's what is denoted here as first quartile, median, third quartile. So you basically have the so-called 25th percentile, the 50th percentile, and the 75th percentile. Whereas the 100th percentile is basically 100% of all the data. So you basically, you have an overall, you have a data set. If you want to have the 25th percentile, that means that 25% of that data is less than that value. 50th percentile means that 50% of that data is below that value. And 75th percentile means that 75% of the data is below that value. That's how you're quantifying this. Yes.
Can you do this in Excel by like through the range? So after you find the calculation of the range, can you put in what is the 20th percentile? Like how do you split that up into 3?
Well, so there are various ways how to do that. One way to do that is the percentile function. Percentile. So there's a percentile is B2 to B41, and we want 25th. So that's, oops. So that's one way to do it. So you can do percentile, use the percentile function. That's not how Nolan and Heinz are suggesting to do that. So they're basically saying, when you have found the median, and you know what the median is, you know what the lower 50% are. And the lower 50% are here, our 20 entries. And these 20 entries you can just easily determine by calculating the median. So basically, you know that the median is here between 20 and 21. So that's the lower range. So now if you want to calculate now the median of B2 to B21, which is 20, you get here the median of the lower 50%. And the median of the lower 50% is basically splitting those 20 entries again in 2 equal 50% parts. So that's the 25th percentile. So that's one way to do it. So we had the percentile function. It comes to the same end. Percentile dot enc is B2 to B41, comma 0.25 for 0.25% fraction. You oh no, it's actually exclusive. Works around it. Okay, so basically it determines the same range. So you have 87.8 as being the median of the lower 50%. So now you have the 50th percentile we calculate as the median. That is now consistent with the median. And then we have the 75th percentile, which is now the median of B22 to B41. So that's the 75%. So now if you think of the interquartile range, so there are several ways how you can depict that. One way is that you say, okay, so so IQR. So the IQR calculated is basically nothing else but this minus this. So you calculate the difference between the 75th percentile and the 25th percentile. So that's one way how to do that. You can also, show 25th and 75th percentile per se. You can see, and that's how I would express it. Yes.
Can you show that for me?
Yes. Mm-hmm. That's just referring to this one. So median is here B2 to B41. That's the 90.15. You can also show this interquartile range by basically saying the IQR is basically 87.8 to 94.3. So I personally, whenever I report an IQR in a paper, I would rather resort to actually giving the lower limit and the upper limit to basically give also an idea about the numerical value, what the in which that interval basically ranges. So that's the IQR. We have a median splitting a 50%. We have 25th percentile splitting the lower 50% in 2 equal parts, and then 75th percentile is splitting the upper part in 2 equal parts. Yes. Exactly. So you create 4 equal parts of your data set. Well, the same median rule applies, right? Good question, because so there are different approaches, and there's no consensus on how that actually is to be approached. So there are, and that's where the problem is sometimes. So Excel basically approaches this mathematically with a function that they're building over the distribution curve. As for calculation, and I shoot me an email, please, on that, because there's an interesting debate that I have seen once to that topic. So there's one camp of statistician that says include that middle value in both upper and lower part and use this for the calculation of the median. And there are some in the camp that are saying leave it out for both. So it's an ongoing debate. So what you will see in statistics, there are some certain things, and we will discuss about that later on when it comes to determining thresholds. For example, when you can use Z-score distribution, the T-score distribution. There's like a recommendation out there by statistician. As soon as you have more than 30 individuals, you can use a set distribution rather than T distribution. But this is not really a hard rule. So there's no convention saying that this is to be done that way. It is an estimate. In the end of the day, everything is somewhat an estimate, and everything is kind of meaning to reflect a probability. So, but yeah, excellent question. Thanks.
How many birds do you find like that?
You mean this?
Yeah.
Well, I have done it here with the median, right?
But you divided up that, like 90, you divided it up by yourself.
Yes, so because it was an equal number for both 50%, it was easy, right? Then it becomes easy. If it were so if you write percentile, if you do the percentile function, you have a percentile excluding and including. So this is percentile dot.esc. So that's excluding. That means that the upper part, that threshold, is basically excluded, and then you have percentile including, that would include it. Both of them are inconsistent with the median approach that Noren and Heinzen recommends, because I did it before. You have 87.7 or you have 87.9. So I didn't want to confuse you. That's why I didn't go further into this discussion. In the end of the day, what you would do in R, you get automatically determined functions that basically would split that literally into a distribution function with an area under the curve. That's what more sophisticated softwares do. That approach is basically just explaining it in simple terms. So the percentile function would basically be how, that's the percentile function is basically how you would quantify this. So this can be EXC B2 to B41 comma 0.25, or they could alternatively be percentile E and C were included. So that's the workaround, right? Excellent question. Okay, so it's percentile.inc or percentile.x exclusive.
What's the difference between EXC and INC?
So it determines whether the value that is the threshold is included or not included. Well, to be honest, I would not at all. I would go with the median approach that we used, because that kind of gives you following the rules. Since you have an equal part, it will take the median, it will take those two middle values and will average those. So it will average here essentially 10 and 11. So that would be 87.6 and 88 or 88. And that will be 87.8. So this is the median approach that we have chosen, and that gives you that estimate. So it's a little tricky. Yep.
What kind of question would you ask us when we have to do this? Would you just go ahead and ask straight, like, from this set of data, find the section?
That could happen, yes. The data will be organized in a way. So some of the questions do have some minor data sets, and then you have like 6 entries or 7, 8 entries to type in Excel and quantify the median, or you do it by hand. But it will be simple. It will be not hard.
Have such a large data set?
No.
Oh.
No. Don't worry. The quiz questions basically aim for a practical understanding of what the data is. It will not challenge you to, okay, so here's a data file with 100 entries. Please give me the median. It's like, no, we're not doing that. Don't worry. No worries. Yes.
I have a question from you.
Please.
How come for the min and max for the median, we did B22 to B41? When you're finding the min and max, don't you include all the values, or that's only for the range?
So the median, what I mean the percent here. So this is the max of, this is the min of upper 50%. And that's the max of the lower 50%.
So when you do the range and you do min and max, then you include all of it.
Exactly. If you do the min and the max and you quantify the range, then you do all data, and then you basically look for those extremes. Any other questions? All right, so then let's continue. So this was we have now the range, the interquartile range, and now we're getting to the most important marker of variability, and that's the standard deviation. And the standard deviation is basically calculated by firstly calculating the so-called variance. So the variance is, now imagine you have this normal distribution, it's symmetric, it's bell-shaped, it's unimodal. You basically have a mean, and now you want to know how do your individual entries deviate from the mean. And the calculation is simple, and here we have again, we have the formula. So I will always, so these formulae, I will always kind of walk you through those formulae and give you a deep understanding of that. So basically what you want to do here, you have an individual X, you have 40 entries, you have one mean. So when you calculate X, each individual X minus M, you get each individual value, and you subtract from that each individual value a constant, which is your mean, which is 90.33. So you get 40 differences. These 40 differences you all square. Why do you square them? Because you have a mean, and it can be, that individual value can be higher than the mean or can be lower than the mean. They're actually equally higher and lower. They need to be arithmetically. So when you square them, you basically have them all positive and squared. So the sign is being taken out. Then you sum them all up, and then you divide them by the number of observations. Consequently, you get some marker of an average squared deviation around the mean. Yes.
Break that down again.
Yep. Okay, I repeat. You have 40 different computations that you do. You have one mean that you have calculated for all your 40 entries, and you have 40 different x values. And now when you subtract from each individual x the mean, you get 40 differences. These are basically greater than the mean or smaller than the mean. So they're arithmetically either positive or negative. So you want to take the sign out of the equation, and you're doing that by basically squaring each individual difference. By that, it becomes squared, but it also becomes all positive. You sum them all up and you divide them by the number of occurrences. That is the variance. That's okay. A backpedal, there's one step before. This value minus the division, just the sum of these squared deviations. So you have a deviation, which is the individual difference, which can be positive or negative. You're squaring that, you get a squared deviation. You're summing them up. You get a value that is called the sum of squares. And that will be super important for analysis of variance, chapter 13 and 14. No, 12 and 13. This sum of squares, and that's just the numerator. Dividing the numerator by the number of observations gets you to the variance. So it's basically the average squared deviation. So it's an average of all squared deviations. Yes, please.
What does the sign mean before the parentheses?
That is the epsilon, that's the sum. Just like with the arithmetic mean, that means sum all individual differences, sum up all those differences. So when we do this now practically, and now I'm inserting again, I'm inserting now I'm inserting now 3 columns with the idea that we have a little bit more space. Good. First thing I want to do, I want to calculate the difference, just the deviation. How much is the individual value deviating from my mean? So x minus m. So when you have x minus m, if the x is smaller than the m, logically the difference will be negative. If the x is greater than the m, the difference will be positive. So if I calculate x minus m, I calculate b2 minus, and now I go here to the right, that's on j, I take the mean, but I need to lock it in, otherwise it would shift down again, don't forget that, right? So you lock it in with the $sign, because it's just one constant. If you do that, you basically get here for the first entry, minus 18.8325. Now, the only thing I have to do, I go to the right lower corner and I again double click, I will complete that all the way down. So now in the next step, and this is where it's getting a little tricky. We only have 4 minutes left. So now I want to square this. So now we have x minus m squared. And this is now equal sign. And you have on with shift 6, you get that little head. So that means to the power of 2. So you're squaring this thing. Once you squared that, you just click the right lower corner and you get again this entire calculation done. If you want to sum this up now, so now we want the standard deviation. We first want to have now the so-called sum of squares. So the sum of squared deviations is now the sum of E2 to E41. That's 1384. The variance is now this divided by the number of occurrences, which we know is 40, right? We know this from here. So we're dividing this now. So the variance of this is 34. If we're going now back to the slide, we have now, lastly, to calculate the so-called standard deviation. And so the middle step of the squared deviations meant to take out the negative sign. You need to do that because if you want to now take that squaring out, you need to use the square root. And if you have negative values under square root, which hypothetically could happen with a skewed distribution, you have an irrational number. So you cannot use a negative sign under square root. So that's why that squaring is so important. You need that step in between to take the sign out. And now basically by doing that, you take the variance, you have this average deviation, this average squared deviation from the variance. You employ the square root, you take the square root, and you get now a standardized deviation from your mean. And that's the standard deviation. And we can do this now for our data set, which is SD, is now the SQRT, and that's the formula. SQRT of the variance gets you a standard deviation of 5.88. So you came from calculating the difference of each individual, the deviation of each individual entry from your mean was positive and negative. You're squaring it, you get then an average squared deviation, which is your variance. And then you take the square root and you get a standardized deviation from that mean. And that's your Markov variability. And sorry, just a second. And what is important, just like with the mean, you have a statistic or a parameter from a population. The statistic is X bar for the mean. The population parameter is mu. With a standard deviation, you have either an SD or an S if it comes from a sample, or you have a so-called sigma, which basically looks like a handwritten O. And the sigma is basically from a population. Sigma square is a variance. Thank you. Have a nice evening. Yes. Yes.
Like 5 minutes later.
Okay, hold on. What's your name?
Schreiber.
My name also.
Yeah, just a second. One of them now. Daniela Schreiber. No, I was told you would come, so I marked you as present. Okay, thank you. Friday, yes. Here you are. All right, sure. Hi. Emily. Okay.
Sorry?
Emily.
Michelle.
Michelle.
Don't worry about it.
I'm sorry.
No,
No, that's not okay.
it's totally fine. You have a lot of students.
Michelle, remind me, Michelle
Steiner.
Michelle Steiner. Okay, sorry.
No, don't worry about it. For when you were doing the standard deviation, I understand the process, but can you just remind me again on Excel what you did to get the first, like when you subtract everything and squared it? Like this I saw and I understood.
Yep.
Sometimes I feel like I'm behind when I'm writing and I don't catch.
Yeah, no, that's fine. And that's why I have the recording.
The recording,
Just a second. Let me just quickly stop that.